Hello, everyone. I'm Nasrin, or typical Zahra Taghiyarrenani. I'm a postdoc researcher at Thompson University, and I did this work with the help of my colleague Mikael. In this presentation, I will talk about a framework for somehow collaborative learning, let's say, and about anomaly detection and classification together. I have the results on the same data that John Berg used, but the learning setting is totally different, and then the results also are different. So for this framework, we have three different topics or three different directions that in one is anomaly detection, model training that can be training from scratch or using pre-trained model, and training paradigm that can be centralized or federated learning. I start with anomaly detection that I'm sure everyone knows that with anomaly detection, we learn the normal behavior, and anything different, we say it is anomaly. But sometimes, and many times, we already know some type of faults. Then why not use them? So let's use the known faults and then train a model. So if we want to use the known faults and generate a model, then it will be a classifier that classifies data into, for example, we have two known faults, classify data into normal, fault 1, fault 2. But again, there is a challenge. What about new faults? In fact, if we want to use a classifier, the problem is that classifier, if we define our classifier with 3 outputs, for every sample, for anything that we feed into this model, it will say it is one of these faults that we know. While, for example, we will have a new fault, and again, it will say it is fault 1 or fault 2. So we need our classifier to detect new faults instead of, in addition to classifying, and also evolve the outputs. For example, if we have a new fault, it should add a new output to it. So in order to have our classifier to be able to detect new faults, our classifier should be able to say, I don't know. For example, in this case, assume that we have fault 1 and fault 2. For every sample, it's the fault 1, either fault 1 or fault 2. We need a mechanism that this classifier says, I don't know. It is not fault 1 or fault 2. And this is what we know as open set learning or open set recognition and machine learning. So it's a combination of classification to detect the known faults and also anomaly detection to detect the unknown faults. But how do we do that? We want to go from fixed classifier to evolving classifier to detect new faults and dynamically add the new faults so that the model evolves instead of staying static. But how do we do that? How we want to force our classifier to say, I don't know. It is based on the confidence of the model. For every classifier that we train, it has a kind of confidence. There are many different criteria for defining confidence. But for all of those, we say if it is high confidence about the output, we will classify the sample as one of the known classes or one of the faults. If it is not confident, then possibly a new class or a new fault is appear. One of the measures for confidence is softmax. We know all that. We usually add a softmax on the last layer of the classifier to convert the data to a probability distribution, right? Then we always have a probability distribution here, and we use the maximum value as the detected class. For example, in this case, the second one is the detected class. We can use this as the confidence of the model. For example, in this case, the confidence is 0.8, or in this case, 0.5. And let's say, personally, if this is one of the best approaches, baselines in the papers that it is called as maximum softmax probability, and it is a way to measure the confidence of the model. But to say, if the model wants to say that I don't know, we need to define a threshold for this. For example, in this case, for every input, it generates some type of confidence. We define a threshold to say that if it is higher than the model is confident. For example, here that we have two classes, we can define a threshold at 0.6, and then if it is over 0.6, it is confident. But there is a problem when we train a classifier that usually our classifiers are overconfident. For example, here, it knows two faults, but our input is fault 3, but still it generates 0.7, while it is an unknown data that has never seen here. And usually because when we train our classifier, we try output to be 1 hot in code, they are overconfident. So in order to have an open set classifier, we need to reduce the confidence of our classifiers. So for example, here we have fault 4, the ideal case. If we try to reduce the confidence, the ideal case should be 0.5, 0.5. It means that the model doesn't know which class it is, or it says, I don't know. But this is the ideal one. We add a threshold here, for example, 0.6. And it's still in this case, because the largest one is below 0.6, it will say that I'm not confident about the output. So this direction of the work is called out-of-distribution detection, open set learning, or open world learning in the machine learning. And we have tried many different methods for reducing the confidence of the models for the unknown samples. And among those, React is one of the best methods. And the good thing about React is that we don't need to do anything with a classifier training. We train a classifier, and then during deployment phase or inference time, we just simplify the latent, and it will reduce the confidence. I will not go into details of this, but after lots of experiments, we found that the React is the best or the most efficient one. So till here, we said that, okay, we have edge, we have the box, we train a classifier. This classifier is able to detect non-class, to identify non-classes and detect unknown ones. But one step further, what if we have many different edges and they can share their knowledge together and they can learn together? That here we go to the federated learning or collaborative learning, let's say. For federated learning, we know that the reason for federated learning, it can be because of privacy. It can be sometimes privacy is not that much important for us, but we want to be efficient in data transmission, or sometimes we just want to share the knowledge between different edges. And here, our focus is sharing knowledge. When a new bus detects a new fault, it wants to announce this fault and inform the other edges that there is a new fault. Okay. But let's back. We have a model here for every edge, and we want to train them. But again, we back to our problem that always have data. We need lots of data for training the model, and specifically here that we want our model to be open source. So we need more data. But what? The first step we have our challenge, and here we are in the age of large models. We are in the age of foundation model. Then why not use them? We have some pre-trained model or foundation model that for language we know, like ChatGPT, and these days we have some of these models for time series. Then we can use pre-trained model instead of training the model from the scratch. So we, instead of training a model from scratch for every edge, we say, okay, let's use those pre-trained models. This just converts the data into some meaningful patterns. And now on top of these models, we just train a shallow model, and it will work. So this is about pre-trained models that these days there are a lot. For example, this is the list of recent models, foundation models, but among those I use Moment. The reason that I use Moment is that it works very good for classification. So I use Moment for every edge. I use Moment as the pre-trained model. I do nothing with that, and then I just add a shallow network on top of that. The network that I add is simple MLP with 2 hidden layers. So this is the setting that we will have for all of the buses. In our example, we assume that we have 5 different buses. All of them, they agree to use Moment. And we assume that, okay, all of the buses have data from normal, fault 1, fault 2 for training this simple model on top of Moment. For this case, I use the same data that John also used with those injected faults. So fault 1 is brake, and this one is engine. So first of all, for every edge, we pass the data through Moment, and we get some pattern. In fact, we get the embed of the Moment. And then step 2 is training this shallow network. This one can be done in federated learning with an average, nothing specific, but the gain that we get here is by using pre-train is that we don't need to pass the whole network, including Moment, just a simple with 2 layers. So in this step, every edge can identify normal fault 1, 2. This is the first result of that. We have, for every edge, we have result as F1 score and area under cap. F1 score is the results of classification performance. It classifies normal, brake fault, and engine fault. And of course, it is a different setting from Jumberg's because it is supervised. Then the result is about 99. I think it is super simple for classifying. And then area under curve is the results for that anomaly detection or for that unknown fault detection. Here, or unknown is gear fault. It is above 8. So now here we had normal fault 1, fault 2. Then we had 3 classes. So the random output is 0.3 for all of the buses. Then every bus defines the threshold. For example, for bus 2, threshold to say I don't know, I'm not confident in 0.4. Then assume this scenario, we pass faulty data from here fault to the second bus. So bus receives the sample, its output is 0.4, 0.3, 0.2. Usual classifier will say it is normal, the first. But it says that, okay, its confidence is 0.4 and its threshold was 0.41. Then it is below the threshold. Then the classifier, the bus classifier or bus 2 is not confident about this sample. And it says probably a new fault is detected. Now bus 2 sends that sample to other buses and asks about their confidence. All of the buses, based on their threshold and the output that they get, should say that if they are confident, which class is that, and if they are confident or not. And they send back their confidence as yes or no to the bus. And then based on the voting on all of the buses, they announce a new fault. Now that a new fault is announced, the edges have to expand the output of their models. For example, if it was 3 or 2, it needs to add one more output. Now it's the models. Now the models need to add this output and again retrain these models. Retraining this model can be done in federated learning. This get average just these 2 layers, not the whole model. There is a challenge again here because the number of the sample that we have for this class is not that much. So maybe we need to do some augmentation for this data set because it was simple for classification. I didn't do, but probably for data set, we need to do some data augmentation. At the end, by evolving these classifiers and sharing knowledge between them, all bosses now can detect the normal fault 1, fault 2, and fault 3. And the F score, the average F score between all of those are 97. So at the end, we had a framework that it identifies known faults, recognizes unknown, and evolves over time. And as a conclusion, if I want to say for this framework, we somehow combine 3 different directions in machine learning. It is open set learning, federated learning, and using pre-trained or foundation models. And I should say that for open set learning, or we know as open set recognition, there are many works for images to detect new classes, but almost nothing for time series. And we at Homestead University, we did a comprehensive work to try different methods for open set learning on over 100 data sets, and even we propose a new method for that. But among all of the methods that we acted as is the best. So this is the whole framework, and by the end of the project, we will more on other parts as well. Yeah, that's.
Any questions? You did one. I think you're good in time. You can afford it.
I have one question. Normal. How do you calibrate that? Or maybe as I would assume it will not remain as from initial what you knew from the beginning. Might be affected by driver behavior or something else that you didn't expect before.
Yeah, in this experiment that we just consider it as fixed, but the thing is that in the framework that maybe we need to work more on that when it wants to evolve again. When we want to add one output, we have to train it again with the normal fault 1, fault 2, and new faults. We cannot keep the same and just add this one, because there is a problem called catastrophic forgetting, and it will destroy the whole model unless we add some techniques. But the initial approach is just retraining everything with this whole classes, and maybe we can get the new normal, and if it has changed, then it will get. But in this scenario, for this example, it is fixed.
But generally, normal definition comes from expert knowledge. What is normal? Not what is. You can add, of course, the definition of faults automatically. Thank you very much.